Welcome to this interactive explainer. Think of this as your hands-on study guide to completely demystifying the invisible physics that govern our everyday world. If you've ever stood there wondering, how on earth do skyscrapers not buckle in the blazing summer heat? Or, why does a simple plastic straw actually work? Well, you're absolutely in the right place. Today, we're going to look way past the surface of the things we touch every day and uncover the hidden laws of matter and heat. Let's get right into it.
Here's the syllabus for our tutorial today. First up, the invisible rules of matter. Then, practice, states and sublimation. Third, forces, density and pressure. Fourth, a challenge, engineering the dam. Fifth, the breathing building story. And we'll wrap it all up with a final quiz, physics in action.
All right, Section 1, the invisible rules of matter.
Okay, let's establish our baseline here. Matter is, simply put, anything that has mass and takes up space, period. Whether we're talking about the massive steel beams of a suspension bridge or literally just the invisible air inside your lungs, it all follows a strict molecular hierarchy, and it's the physical state of a material that dictates how we can actually use it. Look at solids. Their particles have a definite shape and volume because they vibrate in these fixed, tightly packed little positions. That absolute rigidity is exactly why solids are the only materials that can serve as vertical, load-bearing structures. Liquids, on the other hand, well, they keep a definite volume, but their particles slide freely all over one another, which means we have to design specialized containers just to hold them. And gases? Oh, they are wild. Their particles move randomly at super high speeds with almost no attraction to each other. They just expand to fill whatever space they're in, which makes containing them a massive engineering challenge. Honestly, it all comes down to the unseen movement of those tiny particles.
Moving right along to Section 2, practice on states and sublimation.
Now, nature is rarely just static, right? When we introduce energy, like heat, we trigger some seriously fascinating shifts. So I've got a quick question for you. We all know that when we add heat, most solids melt into liquids, and then eventually they boil into a gas. But can you name the substances that pull off a literal disappearing act by transitioning directly from a solid straight into a gas? Take a second and think about it.
The answer? Sublimation. This is just an incredible process where particles gain so much energy so fast that they instantly break out of their rigid, locked structure and completely skip the fluid phase altogether. You can actually witness this happen with things like camphor, iodine, and of course, dry ice, which is just solid carbon dioxide. So the next time you see dry ice doing that spooky smoking thing, you're not seeing steam from boiling. Nope. You are literally watching a solid matter-of-factly vanish into thin air as a gas. Pretty wild, right?
Let's look at Section 3, forces, density, and pressure.
Let's think about the atmosphere sitting right above us. Standard atmospheric pressure is a staggering 101,325 pascals. To put that massive number into a real-world analogy, that is roughly equivalent to having the immense weight of a medium-sized car resting on every single square meter of your body. Crazy, right? Now, we obviously don't feel it because our bodies are biologically built to push outward and balance it, but make no mistake, that atmospheric pressure is a very active driving force in our mechanical systems.
And that brings us to debunking a huge myth. You aren't actually pulling liquid up a straw. Sucking is totally an illusion. What you're actually doing is creating a pocket of lower internal pressure inside that straw, or inside a medical syringe. Then the outside atmosphere, remember that metaphorical car weight we just talked about? That atmosphere does all the heavy lifting. It pushes the liquid down, which naturally forces it right up into the empty, low-pressure space you just created. Creating a vacuum or creating nothingness is literally one of the most powerful tools we have in physics.
On to Section 4, challenge, engineering the dam.
So how do we actually take what we know about liquid pressure and use it to build a safe, stable dam? Well, unlike solid pressure, which is concentrated strictly where two objects physically touch, liquid pressure is multidirectional, and it increases directly with depth. You can see it right here in this formula. P equals H rho G. It shows us that pressure is the product of depth, density, and gravity. Meaning, as you go deeper into the water, the pressure skyrockets, and it's pushing violently in all directions simultaneously.
The absolute crucial takeaway here is that to prevent a catastrophic blowout from all that compounding depth, engineers have to design dams to withstand the maximum crushing force down at the very bottom of the reservoir. A straight vertical wall, it would fail almost instantly. The structure literally must be engineered with a tapered profile. It has to grow significantly thicker at its base
just to push back against the immense, compounded weight of the fluid stacked above it.
Let's shift gears to Section 5, the breathing building story.
You might not realize this, but the structures all around us are not just static monuments. They are constantly moving. But before we get into that, we absolutely have to distinguish between temperature and heat because, honestly, people mix these two up all the time. Temperature, measured in Celsius or Kelvin, is really just the thermal state. It's the degree of hotness. And it's totally independent of quantity. Like a tiny drop of boiling water is the exact same temperature as a giant vat of it. Heat, on the other hand, which we measure in joules, is the actual flow of energy from a hotter body to a colder one. Heat totally depends on the total amount of the substance. And it's this massive influx of heat energy that actually causes physical changes in our infrastructure.
Let's follow a building through a typical day. In the crisp morning, as the sun beats down, the building's materials absorb heat. They rely on something called their specific heat capacity, acting almost like thermal buffers or shock absorbers. This lets the materials take in massive amounts of energy before their temperature rises to a critical breaking point. But by midday, that buffer is completely maxed out. The kinetic energy of the internal particles increases so much that the material physically expands. We call this thermal expansion. Then, at night, the heat energy flows back out, cooling the building down and forcing structural contraction. You guys, the building is quite literally breathing in and out, expanding during the day and shrinking at night. Now, if we didn't deliberately build in weaknesses, this continuous thermal breathing would cause massive infrastructure to literally snap and collapse. It's true. We intentionally engineer gaps into railway lines so the blazing summer sun doesn't just buckle the steel tracks. We calculate a very specific amount of sag for electric utility wires, because if they were pulled totally tight, the cold winter contraction would just snap them right in half. And those massive bridge spans you drive over, they're set on rocker bearings and expansion joints to allow for safe, cubic movement. Basically, we survive by designing for motion, not against it.
And finally, Section 6, Final Quiz, Physics in Action.
All right, let's bring everything we've learned together for a final exam. This is a rapid-fire quiz to test real-world physics applications based on what we've just covered. Try to answer this. How do the three distinct methods of heat transfer, conduction, convection, and radiation, actually operate in the world around you right now? Can you spot an everyday example of each one?
Okay, here is your cheat sheet. Conduction transfers heat through stationary solid particles. Think of a metal cooking pan getting screaming hot on your stove. Convection moves heat via the actual movement of flowing fluids. This is exactly what causes sea breezes and land breezes on the coast. And radiation? That's heat transfer through electromagnetic waves that don't require any medium at all. That is exactly how we're warmed by the sun through the absolute empty vacuum of space.
Next question for you. How do engineers manipulate surface area for huge, solid, heavy machinery versus using atmospheric pressure for fluid tools? Think about a massive crawler crane sitting on soft dirt compared to a tiny little medical syringe in a hospital. How do those two principles differ?
Well, cranes prevent themselves from sinking into the earth by intentionally spreading their immense, heavy mass over a very large surface area using wide tracks. This effectively reduces the pressure per square inch. Syringes, on the flip side, don't spread pressure at all. They actively manipulate it. By pulling the plunger back, you create an internal vacuum, which allows that staggering 101,325 pascals of atmospheric pressure outside to push the fluid smoothly into the barrel.
As you've seen today, from the vibrating particles in solid steel to the massive forces of liquid depth and the daily thermal breathing of our buildings, the universe is just a theater of constant, incredible movement. So the next time you walk across a bridge, or heck, just use a simple drinking straw, ask yourself, what invisible mechanics of matter and energy are working right now in this exact moment to keep your world from falling apart? And if empty space is powerful enough to help you drink from a straw, what else is nothingness actually doing all around you? Keep asking questions, keep looking way past the surface, and thank you so much for joining us for this explainer.